Morning Year 12s. We are going on today to look at quadratics. So you've solved ordinary linear congruences, simultaneous congruences, and it's the same with kind of normal algebra, isn't it? You do linear equations, simultaneous equations, and then you go on and look at quadratics. So we're now going to think about how we might solve this. So x squared is congruent to 7 mod 9. So if we just start by looking at the squares of the integers, so I've just done a table up to 12, that's however much room I had. If I write down all the squares up to 12, 64, 81, 100, 121 and 144. And then what I want to do is work out those mod 9. So I've got 0, 1, 4, that will be 0, 7, 18, so that'll be another 7, that is a multiple of 9, so that's 0, 45, so that's 4, 63, so that's 1, that is a multiple of 9, that's 1, 117, because that's 13 lots, so that'll be 4, and that is a multiple of 9, because that's 9 times 16, so that's 0. So you might notice a couple of things here. Firstly, there are only 4 numbers that appear. So we've got 1s, we've got 4s, 7s and 0s. So we've only got 4 digits appearing there. A second thing, and I'm sure a lot of you thought this at the start, why on earth did I include all of these? Of course, we've got a repeat, haven't we? Because we're dealing with mod 9, we've only got 9 unique integers, 0 to 8 mod 9, and then that's the same as that because 9 is congruent to 0 mod 9, 10 is congruent to 1 mod 9, so we've just got a series of repeats, so didn't need that. And then the other thing is we've got this quite interesting symmetry, so I've got 7, 7, 0, 0, 4, 4, 1, 1, well 0, 0 if I'd have included that 9, so I've got this symmetry happening about the midpoint. So these values, the 0, 1, 4, 7, they are known as the quadratic residues. So quadratic, obviously, because we're dealing with quadratics, residues, I mean, that's kind of like a remainder terminology. So they're the quadratic residues mod 9. Made the point about the repeat, so you only need to tabulate values from 0 to n minus 1. So here, mod 9, you go from 0 to 8. And then we've got this symmetry. So this symmetry, we'll talk a little bit more about it later. Is it unique to mod 9? Well, we're going to come back to that. So I've mentioned this quadratic residues here. What is coming up now is just the official definition. So an integer q is a quadratic residue if it's congruent to a perfect square. So in other words, it must satisfy this congruence here. So x squared, for example 5 squared is congruent to 7 mod 9, so 7 is a quadratic residue. If it doesn't have any solutions, then q is a quadratic non-residue, so it's kind of a bit weird the way that we word this, but we talk about quadratic residues and quadratic non-residues. So we could say here that 0, 1, 4, 7 are the quadratic residues mod 9. And we would say that all the other integers, 2, 3, 5, 6 and 8 are quadratic non-residues. Okay, so nothing really kind of tricky, it's just a little bit of terminology. So now that we've established that, let's go back to this equation here. And in fact, I've got 2. So x squared is congruent to 7 mod 9, and then x squared is congruent to 6 mod 9. So if you were asked to solve this, this would be towards the start of a paper, 3, 4 marks, well, 2, 3 marks maybe. It's expected that you'd list your quadratic residues you need to kind of, be exhaustive about it. You need to make sure that you've checked every single possibility. So here's my table, very clearly marked out with 0 to 8. And then, again, very clearly, because I think some of you, it is very easy maths, but you still need a set method. You need to be clear about what you're doing. So they're my quadratic residues. You identify where you've got this 7 in the table. Okay, well, it is there and there. So I would say something like from table, and you can see I've got only 2 solutions, and then just write them down. So the first solution, x is congruent to, okay, well the 7 is there, but of course I need to go back to the first row. So x is congruent to 4 mod 9, and I've got another solution, 5 mod 9. So it's a quadratic equation, a quadratic congruence, and I've got 2 solutions. That doesn't always hold. I could sometimes have, 3, 4. It's not generally, because it's a quadratic, you've got 2 solutions. This one here, x squared is congruent to 6 mod 9. Well, here I can see that there actually aren't any 6s in that bottom row. So we would say something like, can see from the table that, and use the terminology, 6 is a quadratic non-residue. Hence, x squared is congruent to 6 mod 9, has no solutions. Okay, so hopefully that should be fine. This second example is just to show that we don't generally, we don't always need to use a table. We could just do a little bit of algebra. This says, by considering the expressions 3k, 3k plus 1 and 3k plus 2, list the quadratic residues mod 3. Now, of course, we're dealing with mod 3, so it is so quick. It is so simple to just draw up a table. They're my values of x squared mod 3. That'd be 0, 1 squared is 1, 2 squared is 4, which is 1 mod 3. So we're actually looking at quadratic residues only of 0 and 1. But this is quite a nice algebraic method to consider. Those things, of course, cover all the integers mod 3. So all our integers mod 3 can be expressed as those 3 things. So 3k, of course, is equal to 0, 3, 6, 9, 12, and so on. So they're all the multiples of 3. 3k plus 1, of course, is 1 above a multiple of 3, 1, 4, 7, 10, 13, and so on. And can I fit in 3k plus 2? Not really, but let's try. 2, 5, 8, 11, 14, and so on. So, of course, I've got 0, 1, 2, 3, 4, 5, 6, 7, 8. So what we're doing by considering these 3 expressions is considering all integers. Mod 3. Work out what 3k squared is. 3k squared is, of course, 9k squared, which is congruent to 0 mod 3. If I look at 3k plus 1 squared, so expand that out. Of course, these 2 terms here are divisible by 3. I can, and you're used to doing this in induction questions, aren't you? I can make that even more explicit by just taking out a factor of 3. However, that 1 doesn't go in there, of course, and that is congruent to 1 mod 3. Probably deserves a little comment, particularly, it depends on the wording of the questions, doesn't it? It might kind of say a proof there. This is divisible by 3, hence is congruent to 0 mod 3. You might need that little qualifier as well. 3k plus 2 squared, that'd be 9k squared plus 6k, 12k plus 4. And here, I think I will put a 1 in there. So I've got a 3, and then I've got another 1. And again, that's quite nice because I've got that 1 pulled in with that bracket with the 3. Again, I know that is divisible by 3. So that's going to be congruent to 1 mod 3. So I have used my general expression. I have found my quadratic residues of 0, 1 and 1. So that's it. So I know that squares of all the integers mod 3 are congruent to either 0 or 1. So I've shown that the quadratic residues mod 3 are 0 and 1. Okay, and so I've used a much longer argument than I have there, so remember this little pink table. However, sometimes you will be asked to consider these algebraic expressions there. And it's a method, you know, it's quite a clever method, but definitely if you're just asked to solve something, just list the table. Okay, so modulo 10. This middle column here you wouldn't need to do, I mean particularly for mod 10, even I can work that out in my head, but I've done the table so I'm going to fill it in. 64 and 81. Mod 10, 0, 1, 4, 9, 6, 5, 6, 9, 4, 1. Okay, so my quadratic residues are equal to 0, 1, 4, shall I list them in order? So 5, 6 and 9, I think that's it. It just says find the quadratic residues, do the table. If you wanted to use the algebraic route that we just did in the previous example, we'd have to do 10k, 10k plus 1, 10k plus 2, all the way up to 10k plus 9. So you'd need to have, 10 bits of algebra, which you just aren't required to do. And they would never ask you to do it in that form for mod 10. Note again what's going on with the symmetry. So we have got that 5 is that middle point, and then the 4 kind of corresponds with the result for 6, 3 with 7, 2 with 8, and 1 with 9. We're mod 10. Oh no, look, number bonds. Remember number bonds way back first school reception. So there we've got all our number bonds to 10. And of course there's a reason for that. The reason for that is that 4 is actually congruent to minus 6 mod 10. And squares of those also is going to be equivalent. So you may be asked to do this. And of course this is just talking about this result algebraically. If x squared is congruent to q mod n, so for example if 4 squared is congruent to 6 mod 10, and you know what, this is a little bit odd, isn't it, because I've got that appearing there, so I'm going to change it to the 3 and the 7, I think. So if 3 squared is congruent to 9 mod 10, then 10 minus 3 squared, which of course is 7 squared, that is also congruent to the same thing. So that's just the algebraic form of that statement above there. So let's prove it. Let's just start off with this expression here. Of course, standard thing is to start off with the bit that's more complicated. So if we start with n minus x squared let's do what we can. Let's expand that. I've got n squared. I would have a minus 2nx, and then I would have plus an n squared. And now it's very much like what we were doing on the 3k plus 1. We have got a common factor of n here. We are working mod n. Let's pull out that common factor. I've got the x squared at the end. I know that this here is divisible by n. So congruent to 0 mod n. And all I'm left with is just x squared. So now bring the congruence in, is congruent to x squared mod n. And that's it. So x squared is congruent to n minus x squared, which is congruent to q mod n. So, I mean, it's just a tiny proof, and if this was asked in an exam, it would just be 2 marker, maybe at the start or maybe in the middle of a question. So, slightly more exciting one. We've got a little bit more going on the left-hand side, but we just need to go about as if we were solving an ordinary congruence. We'd subtract 1 from both sides, so that needs to be a congruent symbol there. Note that I can divide both sides by 2, but we need to say why we can do that. 2 and 13 are co-prime, so then I can divide both sides by 4. I'm dealing with mod 13, so let's have a table of the quadratic residues mod 13. So 13, it's a bit daunting, isn't it? But 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I'm going to use the symmetry. So I know that, where's going to be the middle? 7 will be the middle. No, 6 and 7. I'm going to have the midpoint kind of somewhere there on either 6 and the 7. So I've got my x values there, and here I'm looking at x squared mod 13. 0, 1, 4, 9. Here, 16, that would be 3, 25, 25. Crikey, that's 12. 6, 30, sorry, 36, that's 10 above 49, that's 10 above 39 are now. This looks to be where the symmetry is, so I'm expecting an answer of 8 here. 8 squared is 64. 64, is it 12? What am I on? Yes, because it's 52. Yep, so that would be 12. And now, you saw my head hurt there, so let's just go back, use the symmetry. That would be 3, that would be 9, this will be a 4, and that will be a 1. And what am I doing? I am solving this quadratic congruence there. So I'm looking for 4s. I've got a 4 there, and I've got another 4 there. So identify those from the table. Hence, I can see that x is congruent to, of course, I'm not writing down 4, I'm writing down the 2. So my answers, firstly, 2 mod 13, and secondly, x is congruent to 11 mod 13. There we go. So if you're asked to solve this, you must go through these steps. So you must do the table. I know there's going to be, ways of avoiding that. However, please write down your method. Okay, so we're nearly there. I just wanted to show you this last one. One of the ones taken from the book. All of the number theory stuff that they do is very minimalist in the online textbook. Here, prove that this congruence mod 8 has got no solutions. So the word proof, it sounds like, and you've been trained to think of that as being, quite a kind of strong word, need lots of kind of rigorousness in your solution. However, all you need to do is go about solving it. Write down a table, show all the possible values for mod 8. We've just got 0, 1 and 4. 0, 1 and 4, so 6 is a quadratic non-residue. So said here from the table, there are no solutions satisfying that, and that's it. I think I would probably add that 6 is a quadratic non-residue, hence no solutions. But you might think at first that that word proof means you need to go down to the algebraic root. All you need to do is find all those quadratic non-residues, so all the quadratic residues, and you can clearly see that 6 doesn't apply. So questions from the book. This is exercise 2C, 15 to 18. These won't take long. It's just a matter of kind of doing a few tables. There's a couple of things that you need to think about, and even these kind of solving ones here aren't particularly tricky. Okay, I'll see you tomorrow.